From neutrinos to gravitational waves, that is the subject which I wish to address today. What I've shown here is the history of my research. In 1981, I went to graduate school. As introduced earlier, I joined the Kosiba Institute in Tohoku University, and it was a preparatory stage, but I was participating in the Kamiokande research, and that started my life as a researcher, and I have continued research until today in 2020. As you can see from this table, Kamiokande or super Kamiokande neutrino research was my central research, and I continued that. But after I moved to study gravitational waves and Kagura from 2008, and the overall flow I'd like to describe in the allotted time, which is 30 minutes. And now, as to the location of the experiment, perhaps you are aware, Kamiokande or super Kamiokande and Kagura in Hida City in Gifu Prefecture, in Kamioka, there are experimental facilities. On the map, that's where it is. And if we show you a photograph, that this is what it looks like in 1980s. In the early 1980s, this picture was taken. And you can see the mountains, and on the very right-hand side, at the foot of these mountains, you have Kamiokande and also Kagura. If you look closely, in the middle of the mountain, you can see some facilities. It's a mining facility, and when we started our experiment, we started with facilities in the former mining area. And so I'd like to address the research of Kamiokande and super Kamiokande. Kamiokande and super Kamiokande is where we have mainly done neutrino research. Some of you may know what neutrinos are, but I'd like to briefly introduce what it is. Neutrinos is a form of elementary particle. As to what kind of elementary particle it is, from electrons, electric charges and mass have been, for the most part, excluded. Excluding charge is very difficult, and so because of this characteristic, it can penetrate almost anything. It can penetrate the Earth even. But thankfully, very rarely it hits matter, and so we observe taking this very valuable opportunity, and that is how we have done neutrino research. And there are three kinds of neutrinos. And for a long time, it was that there was no mass. And as to how to do research on neutrinos, the neutrinos are such that you can't see it. You can try as hard as you can, but you can't see the neutrinos itself. So how do we do research? Sometimes it hits nucleus. And then there will be particles with electric charges, elementary particles with electric charges. And when this runs, we have means to measure this. And Kamiokande and super Kamiokande are such that the nucleus is a nucleus within water. So the particle runs through water, and when this is done, the particle emits light, and the light can be detected in many ways. Light detectors are used to detect light, and the neutrino response can be researched in this way. Now, the super Kamiokande is the main subject of my talk today. But very briefly, I'd like to talk about the Kamiokande experiment. Kamiokande was originally was predicted in 1970. That is proton decay. Proton has a certain lifespan and decays. And the Kamiokande was an experiment to ascertain that. And for this purpose, in Gifu Prefecture, Kamioka, 1,000 meters underground, you needed to do a lot of research. So 3,000 tons of water was in the detector. Within the 3,000 tons, there are lots of protons. And so one of this we felt would decay. And we wanted to find that one that decayed. But unfortunately, the proton life was longer than predicted earlier. So at Kamiokande, with Kamiokande, we couldn't observe proton decay, and we couldn't discover it with the super Kamiokande as yet either. On the other hand, with Kamiokande, a supernova neutrino explosion was observed for the first time. And neutrinos from the sun, and spacecraft, cosmic rays, neutrinos. These could be discovered. And we discovered that it did not match what was predicted through theory.
So we found out through Kamiokande that neutrino seems to be very important. So after this, we moved to super Kamiokande. And today, the father of Kamiokande, I'd like to introduce Professor Kosiba again. Dr. Kosiba, unfortunately, passed away on the 12th of November. So Dr. Kosiba had the idea of Kamiokande. He thought it was important to have firm results from the Kamiokande experiment. So he decided to develop a photodetector of a diameter of 50 centimeters, which was never seen in the world until then. So Dr. Kosiba himself decided to develop the world's larger photodetector or light detector. And the success of development of photodetector led to the success of Kamiokande. And in 1983, experiments started. But when the experiment started, proton decay was not observed so frequently. And at the same time, we found out that the functional performance of this photodetector developed was very good. So Kamiokande was remodeled, and a few months after the experiment started, he proposed reforming or refurbishing Kamiokande, and the team remodeled the device. And in 1987, February, we observed the supernova explosion neutrino, and were able to restart the experiment about 2 months before that. So he has a vision or insight about the future. Unfortunately, he passed away on the 12th of November. But for us, Professor Koshiba's vision about the future, we hope we can continue to take after his vision. So neutrino was found to be interesting through Kamiokande. So Dr. Koshiba proposed a super Kamiokande. And actually, now super Kamiokande is under operation. And as you know, super Kamiokande has a diameter of 40 meters and a height of 42 meters with 50,000 tons. This is a large neutrino device. And this photograph From 1991 to 1996, Super Kamiokande was constructed during this period, and this photograph was taken at the last phase of a construction, so the instrument is already almost being made, and clean water is inside this measurement device. So the photograph was taken then. It was around January 1996. And from April this year, the experiment started. And with Kamiokande, cosmic rays or neutrinos made on the atmosphere was found to be strange. So the experiment spent a lot of time in looking and researching about neutrinos. As you can see here, cosmic rays comes in the atmosphere and hits the nucleus or atoms, and that leads to the creation of pions. And through that process, neutrinos are created. And Super Kamiokande, about 10 neutrinos can be observed every day through Super Kamiokande. The neutrinos are analyzed, and in June 1998, as you can see on the left slide, we are able to acquire this data. This is about mu neutrino. The direction that neutrino came from is cosine theta equal 1, which is downwards, and -1 is upwards. So this is a neutrino coming from the other side of the Earth, and 0 is our ones coming from the side. So based on direction, how much neutrinos are coming, this compares the data with the actual forecast. The neutrino going downwards, about 10 or 20 kilometers above our head, these neutrinos coming downwards, the data matched with our assumption, but the ones coming from the other side of the Earth that flies for about 10,000 kilometers, then it was about half compared to the expectation. As shown on the right-hand side, after a long distance, because of neutrino through oscillation, changes from mu neutrino, tau neutrinos, or vice versa. So as a result, it is half. So the neutrino oscillation in 1998, the neutrino oscillation was discovered. And later, today I don't have much time, so I will not cover the details, but neutrino research developed, continued to develop after that, and now we wonder whether neutrino is the source of matter on the universe. Is that related to matters in the universe? To confirm that, the new generation neutrino studies are going to start. This is in Tokai-mura J Park accelerator. Neutrinos, and on the other hand, antineutrinos are made, and they are about 300 kilometers apart. The new Kamiokande, 300 kilometers far away, is going to be constructed to make the observation. And the hyper Kamiokande volume is about 10 times larger than Super Kamiokande and has a higher performance as a detector. And with this device, neutrinos, neutrino oscillation, and other neutrinos, neutrino oscillation will be observed to see whether any difference, and we want to challenge the question of a source of matter in the universe. The device construction started this year, and we plan to start the experiment around 2027. However, I myself recently am rather aiming at studying the gravitational wave astronomy, and I'm participating in the Kagura project. My title is From Neutrino to Gravitational Wave, So I'd like to use this page to talk about it. In April 2008, I became the director of Institute for Cosmic Ray Research, and until then, I was also doing a lot of research, but as I became a director, it's not possible to concentrate only on research anymore. And at the same time, cosmic rays creating neutrinos in the space, I have been studying that for more than 20 years. And studies of neutrinos, I personally thought that I could reach a conclusion by myself, so I was interested in doing something new. And at the time, at the Institute for Cosmic Ray Research, a gravitational wave project was considered to be the most important challenge for the research institute after neutrino studies. Of course, I personally was also interested in gravitational wave science. So, on this occasion, I started to participate in the Kagura project. And in this way, from 2008 to 2010, I shifted from neutrinos to gravitational wave. This diagram is in Hida Kamioka area, mountains, how the devices are being allocated. Super Kamiokande is in the mountain, and in the same mountain, the laser interferometer of Kagura is installed. And this project, in 2010, the project started. And when the project started, of course, there was no tunnels. That was the situation that we started.
As can be shown in this photograph, 4 years and a half since the start of the project, 2015 in February and in March, the tunnel had been dug, of course, and 3-meter arm vacuum pipe had been laid, and we have completed the test. And let me say that with regard to gravitational waves, Professor Weiss will be speaking about it in detail. So I'd just like to talk about the project and I restrict myself to just explaining, giving an outline of the project. The Kagura is such that it's a unique device. It's underground, and where Earth vacillation is small, and we can conduct conditions under such circumstances. The most important mirrors, the 4 of them, minus 253 degrees, 20 Kelvin. That's the mirrors are cooled in this way, and that is the kind of a device. Why do we cool it to 20 Kelvin? The mirror is a matter, and there is a heat movement, and the surface of the mirror will slightly sway, and it will be noise for the observation of gravitational waves. So we want to reduce the motion and of the mirror as much as possible, and that is why we reduce the temperature. And so for this purpose, for the mirror, with regard to the mirror, we were particular about the material in cryogenic circumstances where the performance is good, and we have selected sapphires for this purpose. And on the left-hand side, you see a photograph of the sapphire mirror. The diameter is 22 centimeters, thickness is 15 centimeters, and the weight is 23 kilograms. On the right-hand side, this is underground. Within the vacuum container, the mirror has been installed. This photograph was taken November 30th, 2017, when the first mirror had been installed. When we finished installing, that was a commemorative picture taken then. And you can see the number of people involved in installing just one mirror. Anti-seismic devices were used, and it was installed so that cryogenic cryogenic conditions could be met. And so we needed this many people. And Kagura, the experimental group I'd like to introduce as well. Kagura is an international joint experiment centered around East Asia. There are about approximately 400 persons participating. This photograph was taken last year in August, and at the Tohoku University, we had a joint meeting. We had a meeting of the international joint research group. So we took this opportunity to take a photograph. And so it's a joint international effort in pursuing the Kagura project. And this is the laboratory or the experimental room. It's the central experiment room. And in the middle of this photograph, there's a vacuum tank, and there's a beam splitter inside. It half reflects a laser light and half allows the laser to penetrate. That is the kind of mirror this is. And what has gone through or reflected from here goes to the 3-kilometer arm. So in this way, finally, last year, we have completed construction, and this spring we started observation. After that, I'm sure you've seen this photograph several hundreds of times, or several 10,000s of times. As you can see, this is the coronavirus, and there was an emergency declaration as a result of COVID-19, and nobody could come to Kamioka. And the people on site were doing their best, but the number was limited, so that the 24-hour operation over the long term was limited. So we suspended after having observed for 2 weeks. And presently,
COVID-19, after COVID-19 settles down, we hope, then we would like to start the next observation. And this is the world's laser interferometers map. There are two in the United States called LIGO. I believe Professor Weiss will talk about it. And also in Italy, there's Virgo. And far from these two, Kagura is located in Japan. And in addition, in the late 2020s, LIGO, the third LIGO, is expected to be installed in India. The point here is that Kagura is far from Virgo in Europe or LIGO in the US. This is an important point. And in the future, Kagura, LIGO, and Virgo will do joint observations. When we make joint observations, what is important is that Kagura is located far away. A gravitational wave will achieve at the speed of light. But the time of arrival of a light, by comparing the three data, we can know from where the gravitational wave is coming from. And actually, by having the participation of Kagura, we'll be able to enjoy high precision in determining the direction of the wave. Now, in 2022, Kagura is aiming at participating in international joint observation. And we're making further developments or improvements of the device, aiming at 2022 participation. And the last point the mystery of the universe researched through gravitational wave. Where is a gravitational wave coming from? What we are thinking about by using this device is shown on this slide. From the left, neutron-star binary merger. Two neutron stars binary by merging. What is interesting is that heavy elements like gold and platinum are made when that happens. And actually, in the observation data of 2017, there was a strong evidence already being reported about it. So for this, further observation will be increased to see how such heavy elements are made in the universe. And the one in the middle is the black hole binary merger. Since the universe was born, merger of black hole binaries, what is the frequency that this has happened in accordance with the years in the universe? And observed black hole were heavier than expected. So how are these black holes being made? That is another point we want to understand. And lastly is a supernova explosion. What the explosion at the end of the life of a massive star? We want to understand well how a star will end. So these are our targets in terms of astronomy going forward. Now, today, first I talked about neutrinos, and then I talked about gravitational wave. But actually, neutrinos and gravitational waves, neutrinos and gravitational waves observation can be done in cooperation. That is what is important with these devices. If we can make observations of a supernova explosion, the mystery of supernova explosion, or the source of elements in the universe can be understood. So, conclusion. Kamiokande, super Kamiokande, throughout the many years of studies, it was discovered that neutrinos' mass is small, and the small mass of neutrinos may tell us why we or matters exist in the universe. So, I'm also looking forward to future neutrino studies as well. On the other hand, for black holes, the situation of a universe that cannot be researched through light, a new gravitational wave astronomy has just started, as Professor Weiss will be introducing to us. And Kagura started its observations this year, but because of COVID-19, the observation was suspended after only 2 weeks. And now we are making preparations as much as we can for the next observation, so I'm looking forward to your support. So this concludes my presentation.